Good evening, everyone. Welcome to the week 2 of NPTEL problem solving session. I am Gitanjali Singh, your TA for Medicinal Chemistry. I am a PMRF from Department of Chemistry at IIT Kanpur, and this is the second week for this problem solving session. Let's start now. This problem solving session will be held every Monday from 6 p.m. to 8 p.m. It will be live on Gmeet. You guys have been shared this link, and this link would be active for upcoming 11 weeks. This session will be recorded and the link would be shared with you after the end of this session. In case of network disruption from my side, please stay online. Do not leave the session. I'll try to join back as soon as possible. Now, for this week's session, we'll discuss the week 1 assignment and along with a brief preview of what has been taught in the second week. The things covered in second week are enzyme catalysis part 1, enzyme catalysis part 2, tutorial which included binding forces, protein structure, functions, introduction to receptors, receptor types and function, and finally fourth tutorial which included receptors, binding interaction, and ion channels. I'll not summarize all the topics. I'll see how long we can stretch this class. My focus would be the assignment solving and your approach towards solving the assignment. I'll try to discuss all the basic basic terms and basics of the assignments. So let's start now. Please, if you have any question, please you can unmute yourself and ask the question if you want that urgently, or you can type it in the chat box. I'll keep on checking the chat box at regular intervals, but even so, you can unmute yourself and ask the question directly. So, question number 1. Which of the following shows increasing order of acidity in alcohols? Guys, this is alcohol. You are given 4 options. You have to decide which one is the strongest and in increasing order. That is from smallest to highest. Try to put your answer in the chat box so that I can get an idea, what you guys are understanding. I am audible, right? My voice is clear and you can understand everything that I say. Perfect. Now go ahead with the question. Okay, do you want me to start solving the question? Let's see. See, can anyone tell me how alcohols behave, like base or acid? Sorry. Guys? Hello? Write down, just a minute. When alcohol is reacted with a base, say sodamide, NaNH2, it forms an alkoxide minus Na plus plus. You guys can see this, right? Now this alkoxide ion with Na as a counter ion is a base. Now this is the kind of base that this alcohol forms. You have to decide what kind of alcohol has highest acidity. Okay, the simple factors responsible for acidity is called CARDIO. C stands for charge, A for atom, R for resonance, D and I dipole dipole interaction, and you can just forget that, and I for inductive effect, and O for orbital. Now I've made a slide for you guys just to see. I'll just try to zoom it. Yeah. So the when let's talk about the first factor, that is charge. Wait a minute, guys. Charge. You see, within the acidity of an atom with increase in charge increases. You know. Hello. Hello. Am I audible? Hello. I'm sorry. Am I audible? I'll continue anyway. Okay. With increase in charge density, that's mostly positive charge, the acidity of the compound increases as well. Now, yeah, as you can see from an example here, with increase in the positive charge, this is neutral H2O. You can notice the pK value here stands 14, and for H3O plus it's minus 1.7, whereas that for I've not mentioned for like OH minus because it's mostly basic. Now again, the pK value of NH3, which is neutral, is 38, whereas after the addition of single positive charge, that makes it NH4, the pK decreases to 9.2. Lower the pK value, higher the acidity. Now see, that's when there is charge. When the second factor for the from the cardio is atom, this A for atom. Now, as we know that electronegativity increases the acidity. Why is that so? Take an example here. They have taken this carbon, nitrogen, oxygen, and fluorine example. You see the chi value, the electronegativity increases from carbon as we move towards nitrogen, oxygen, and fluoride. I'm saying fluoride because after HF, after losing H, it becomes F minus. That's why I'm saying F. Please, if you have any confusion regarding the terminologies that I'm using or anything like that, please ask me at that point so that there is no confusion or miscommunication between us. With increase in electronegativity, you can see the pKa decreases from CH3. The class starts at 6 p.m., so I think it has hardly been 5 minutes or maybe 10 minutes. Yes. So now atom, when we move down, uh, yes, sure. Okay, I understand. That means you might be running a week late. Don't worry, you already have recorded session and problem solving sessions, and the links are already shared in the public data sheet. If you have any doubt, you can go back and refer to it. And today I'm discussing very basic things. I'm mostly solving the questions from assignment one. If you have any problem regarding the things that I'm discussing right now, please feel free to ask. And if not, you already have recorded session for the previous sessions, and even this session will be recorded, so please don't worry about it. You are not lagging behind. You can easily catch up. Where was I? Okay. um, Atom, the electronegativity of the atom. Yes, the electronegativity of the atom, with increase in electronegativity of the atom, acidity also increases. We know along the, as as we move. uh, yes. Okay. Yeah, as we move down along the periodic table, we see the size of the molecule decreases, electronegativity increases. So, in general, the acidity of the compound also increases. While moving down the periodic table, we see the size of the elements increase, nucleus increase, because of the addition of different shells. That makes that basically makes it easy for the atom to polarize it. So increase in polarizability makes it easier for the compound to lose edge, and losing and the easiness with which the compound loses edge, I mean, how easy it is for a compound to lose it, makes it more acidic. So as we move down the periodic table, the acidity also increases. So from moving from left to right, acidity increases, and even moving from top to bottom, the acidity also increases. The third factor from cardio is, we are done with charge, we are done with atom. Now R. R here stands for resonance. You see, resonance basically means delocalization of the lone pair of the atom um, along the compound. So basically, more the delocalization, more is the sep stability, and hence stabler is the conjugate formed, and hence the acidity also increases. You see the example here. One is phenol and one is not aromatic. There is no delocalization for the oxygen. Let me use different color. You see the lone pair of oxygen here has nowhere to move. It is present on oxygen and it stays there. Whereas the lone pair here in phenol, it's, it can move like this can move like this, and it can come here. So the lone pair has got, ample area for it to delocalize, hence make a stable, it can stabilize the conjugate after losing this edge here. So it makes the compound more acidic. Now dipoles or inductive effect. We are done with this. Dipoles or inductive effect. Don't think about this. Forget about this. The inductive effect is an important factor here. Let's consider this. Now, inductive effect has two type of effect: electron withdrawing and electron donating. Electron withdrawing elements, are electronegative elements that basically try to pull the electron density towards itself. Once it starts pulling electron density towards itself, it becomes easier for the compound to lose H, because the density shifts from H towards the more electronegative atom. Once that happens, it's easier for the compound to lose H, and easier it becomes for the compound to lose H, the more acidic it becomes. The opposite happens with electron donating group. What electron donating group does is it starts increasing the density. It starts pushing more electrons towards the H. Now, once the density of electron is more towards H is reluctant to leave the compound, and this reluctance decreases the acidity of the compound. And finally, O. This O here stands for orbital. You'll see this has let me remove this. Now, O for orbitals. The closer, let's talk about hybridization. So there are different types of hybridization: S, P, SP2, SP3. What we do is we try to find the S character and proportionate P character. In SP, it's 50-50%. In SP2, S character is 33%. P character is 66%. So basically, with increase in S character, the acidity increases, and the compound becomes more acidic. So now let's try to solve this question here. We have seen all the factors. Now try to solve this again. O minus in the first option, we don't have a, we can see that it's O minus for all the options. So we don't have to consider C or A. There is there is no other element other than carbon and oxygen. So we don't have to think about charge. We don't have to think about atoms. Now let's think about resonance. There is no resonance in one, but I can see there is resonance in other compounds. Is there resonance in second one? No, because there is no conjugation. There is no conjugation. There is nowhere for this lone pair in this charge and the lone pair in high oxygen to move. So there is no resonance for B. It's for 2. Let's check in 3. So now it can What about in the fourth option? Again, there is no conjugation in fourth as well, so no resonance here. So now we can say that the third one has the highest acidity. What about the other one? Let's consider the other option, inductive effect. Because there is no other atom here, we don't have to think about inductive effect as well. The last option is to check the hybridization. This one is sp2 hybridized, and this one is sp hybridized because of the triple bond. Now we know the sp hybrid has more acidity compared to sp2. So third is most acidic, followed by the fourth one, then the second one, and finally the least acidic one is first option. Yes. You guys got this one right? Is it clear to everyone? Give me a thumbs up or anything so that I can move towards the next question. I can move forward to the next question. We have discussed this resonance, inductive effect, and orbitals. Let's solve the second question. Now, again, this question, it's based on the same concept that we discussed. Take a time and just try to apply what we just learned. Which of the following correctly explains the trend in acidity of hydrohalic acids? Hydrohalic HX, where X is a different kind of halogens in the aqueous solution. The options are HF, HCl, HBr, HI. Again, you can keep the cardio in your mind. C, that stands for charge. You can see there is no charge here, and if you would consider charge after the dissociation, the charge will be same in all the compounds because these are all hydrohalic acids. F minus, Cl minus, Br minus, I minus. So there is you don't have to consider charge here. A, atom. You see the atom is changing. Apart from H, you see there is change in the hydrogens, I mean the halogens. So F, Cl, Br, I minus. Now think about the trend, how acidity changes when we move from top to bottom in the periodic table. Is there any answer in the chat? Yes, try to attempt it. If not, I'll solve this one as well. Okay. Yes, perfect. You all got the right answers. It is correct. As we move down the periodic table, we see the size of the atoms increase, and it's easier for them to stabilize the electron density, the charge density that they have over themselves. And you know the decreasing bond dissociation energy also helps, and hence hi this hi is more acidic than hbr, which is more acidic than hcl, which is more acidic than hf. So yes, B is the correct answer. Now let's move towards the next one. Which carboxylic acid is more acidic? Now look at the options carefully. There are four options. You see, The different thing here is they have actually added a substituent, which is chlorine. You don't have to think about. Yes, very good. I can see people being more active now. Very good. So you can think about Cl and its placement. Now, you don't have to think about charge atoms. Okay, there is one substituent which is not present in first, but in the rest of the three options, Cl is added as a substituent. There is no resonance, obviously, that should be considered. Now, inductive effect. Cl is electron withdrawing or electron donating. Anyone? You can unmute yourself and give me the answer. If not, just put it in the chat box. Good. Yes. So Cl is electron withdrawing, and we know that once electron withdrawing increases the acidity of the compound by trying to, um, you know, pull the electron density towards itself. Now, the placement here is also important because inductive effect depends on two factors. That is the kind of substituent, that is Cl, which is same, and now the distance of chlorine from the main group, that is carboxylic acid here, because carboxylic acid loses an H to form carboxylate ion. There's I'll just oh, I'm sorry. I'm sorry for the congested writing for the fourth option. You see the substituent in 2 is on second carbon. In third option it's on third, and in fourth option it's on 4. That since the distance keeps on increasing, that means the acidity, the effect of electron withdrawing group will also decrease. Hence, the most acidic among the four option is B1, due to the placement of chlorine just next to carboxylic acid. Now, let's look at this one. Which compound is most acidic? H2S, CH4, H2O, and H3. Let's recapitulate um, you know the concept that we just um, revised. C, charge. You don't have to think about charge because there is no charge species here. Atom. Now the atom changes in all. There are different atoms in all four options. You have to see how the change in how different atoms are behaving there and what is the trend of acidity among these options. H2S. how acidity changes from when we move from left to right along the periodic table and from top to bottom. These are your hints. Okay. Yeah, good. I think you guys got understood this concept pretty well. So yeah, as you move along the periodic table, the acidity of the compound, you know, decreases and then increases, sorry. As you move from left to right, it increases, and as you move from top to bottom, it increases as well. You can see. Yes. Yes, Shyam. You can unmute yourself and ask the question if you have any doubt here. If not, I'll just continue. Okay, very good. We're done with this question as well. Let's move to the next question. Sorry, what's happening? What is meant by ADME in pharmacokinetics? So the concept of you guys are aware with the concept of pharma. Very good. Yeah, good. Yeah, everyone is right. The option is B: absorption, distribution, metabolism, and excretion. Yeah, perfect. I'll just explain it briefly because, for later, for reference, for people who will join for people who will watch the live class. ADMA in pharmacokinetics. Pharmacokinetics is is basically what happens once we have this medicine. Once we take a medicine, what our body does to the medicine. That's called pharmacokinetics. Now, the first thing that happens is you the medicine, it's absorbed and it's basically, absorbed in the bloodstream. From this bloodstream, it is distributed to different parts of the body, and it reaches its target. Once it reaches its target, it is metabolized. It basically does its work, and then after the work is done, we no longer need the medicine. It is then the the byproduct or medicine on its own is excreted from the body. That is called ADME in pharmacokinetics: absorption, distribution, metabolism, and excretion. Okay, good guys. Let's move on to the next question. I don't know what's happening. Okay. What type of structure is present in A and B? So let's look at these structures carefully. We know about nucleic acids, and yeah, perfect. Good. Yes, the answer is purine. So let's discuss briefly on what is purine. The options that the different options that we have constitute purines and pyrimidine. So let's see what purine and pyrimidine is actually. Pyrimidine is basically, six-membered ring with nitrogen atoms at position 1 and 3. These positions can be, you know, let me write this. Change the color. Sorry, I've written pyrimidine in the second option. You can see 1, 2, 3. So purines and pyrimidines, they are basically nucleic acids that make our DNA and RNA. Now pyrimidines are basically a heterocyclic ring in which nitrogen is present in 1 and 3 position, whereas purine is hydrocyclic aromatic carbon. It's basically made up of pyrimidine and an imidazole ring. You can see here. This is the pyrimidine ring and this is the imidazole ring. They both together fuse and make purines, and these are the options, adenine and guanine, thymine and cytosine. They are present in DNA. In RNA, thymine is replaced by uracil, which is less stable due to the absence of CH3. Thymine is more stable than uracil. We'll read more about this in the upcoming week. But just to get a basic idea of structure, you have to remember this: how purine, what the structure of purine is, what the structure of pyrimidine is. Just a very basic idea for you to differentiate between these structures. Now, quinoline. Quinoline is again, benzene fused with pyrimidine. You can see the structure here. This is pyridine, this is benzene. They are fused together to form quinoline. It's a very common scaffold in medicinal chemistry. You'll read about it more in upcoming lessons. And naphthalene, it's a polycyclic carbon ring. These are very, very basic scaffolds used in medicinal chemistry. You'll see this as a repeating unit in almost you know, all the medicines that you read about it, read in leader classes. Let's move on to the next question. pKb of NH3 is 4.75. Which of the following statements are incorrect? Are they, just one of the statement is incorrect, but let's see. NH3 acts as a strong base. Number 2, NH4 is a conjugate acid of NH3. Third option, pKa of NH4 plus is 9.25. Or fourth option, all of the above statements are incorrect. Now, Kb, let's this is what Kb is. Kb is basically the measure of basicity. Higher the Kb, greater the basicity of the compound is. But when we put pKb, when we think about pKb, it's minus log of Kb. The higher pKb indicates lower basicity. So if the if pKb is low, the basicity should be high. What is 4.75? Is it low? Is it high? And what does it mean? Yeah. So, good. Everyone is right. NH3 act as strong base. We know NH3 with pKb of 4.75 is not a strong base, it's actually a weak base because NH3 uh, in present in aqueous medium does not dissociate completely. It just now we can see NH4 is conjugate of NH3. Well, that's right. pKa of NH4 is 9.25. Okay, that's fine, that's also correct. But because NH3 is a weak base, and it here states that N. Okay, I'm sorry. Am I audible now? Am I clear? Is my voice clear now? Okay, perfect. So the option A here is incorrect. NH3 is not a strong base, it's actually a weak base, and rest of the options are correct. Again, this is now. Let's move on to the next question. Which of the following atom in the structure below is likely to be the strongest hydrogen bond acceptor? You have to look at the structure carefully. Try to see that which is uh, more hungry for hydrogen bond acceptor. Yes, like which can accommodate hydrogen easily, just more hungry for hydrogen. Yeah, good. Yes, that's the correct answer, carboxylate ion. When you talk about hydrogen bond acceptor and donor, we try to see which of the functional group there is more hungry, when it as hungry and when it can accept H bond easily. That means H easily, it acts as a hydrogen bond acceptor, and when it's easier for that functional group to donate hydrogen, it makes a good hydrogen bond donor. In this case, we can see there is a carboxylate ion. There is a negative charge on carboxylic acid. So obviously, D is the correct answer. It acts as a better hydrogen bond acceptor. Let's move on to the next question. Phase 3 clinical trial is a lengthy process and carried out in few thousand diseased individual. Is it true or false? Now let's recapitulate different phases of clinical trial. Are you sure it's false? Try to remember how, uh, what are the different phases: phase 1, phase 2, phase 3, and phase 4. They're not, you know, talking about phase 4. When we generally talk about clinical trials, we don't exactly consider phase 4 because that would include FDA. We don't talk generally in considering Indian market as main. We talk about FDA approval because we talk keeping American market as a reference. So for just for this text, let's see. Phase 1. Let's just recapitulate what is phase 1. Phase 1, the length of time is from few months to maybe a year. It does not take 1 year, but you know to 1 year, from few months to a year. What they do is uh, they collect a volunteers, a group of volunteer from like 20, 40, not even 100, less than 100, and they try to see the dosage, the quality, and these are healthy individuals. In phase 2, what they do is they uh, they they I'm sorry, they they give this medicine to a group of like 100 or more than 100 diseased individual. Here they see how how this is affecting them and what's happening. And in phase 3, which is usually longer than phase 1 and phase 2, they take a larger group of diseased people, and they learn about all the other things like side effects and the dosage and how it treats the disease, things like that. Phase 4, it can take up to so many years, and sometimes they don't even get approval for the market. They just leave there. So yeah, the correct answer here is true. It is quite a lengthy process, and it's carried out in few thousand diseased individuals. Let's move on to the next question. What term is used to signify a preparation that appears identical to the preparation of an active drug but has no biological activity? Yes, I can see the answers. Very good. Yes, it is actually option C, placebo. The dummy drug. um, I'm sorry, to move back to the last question. I have a question in the chat box. Will it not conducted in healthy individuals? No, phase 3 is not conducted in healthy individual. Phase 1 is they generally do this test, the healthy individual test in phase 1, where they are volunteers. Phase 3, they conduct this study among diseased people. That's like the final thing that goes before um, sending the thing to market and for further approval from FDA. So no, and phase 3 is not for healthy individuals. Yeah, we were discussing about placebo. Now, so placebos, they generally use placebo. Like what they do with placebo is a group of a section of population of volunteers, they are given this medicine, and half of them are said that they are given a medicine, but they are not actually. They are given some kind of sugar or something, like they're told they are given medicine, but it's not actually medicine. Just to check, just to see whether it's the work of the drug is psychological or it's actually giving some kind of effect to the population. So placebos are often used in clinical trials as an inactive control, so that the researcher can better evaluate the true overall effect of the experimental drug treatment on a study. Most of the time, even the researchers are not told whether uh, which group of people are given placebos and which group of people are actually given the medicine. So this placebo is just given to eliminate the biasness. So yeah, that's placebo. Dummy drug, they don't use this term dummy drug. More or less, placebo, dummy drug is not a scientific term, and they don't use that dummy drug. Peptidomimetic, it's actually a drug made from peptides, and they have some kind of activity. It's actually very good and a very This branch of science has a very good potential. It's People are trying to develop drugs based on peptide that mimic the good things about peptides, like biocompatibility and things like that, and have a very good activity as a medicine. So that's peptide. But they said does not have any biological activity, so that peptidomimetic cannot be the correct option. Placebo, that's right. Gazebo, it's basically a hut kind of thing. It has nothing to do with medicinal chemistry. Let's move on to the next question. Identify which of the following terms refer to the order in which amino acids are linked together in a protein. Very good. Yes, it is. Sorry. Yes. Yeah, I see everyone is right. It is primary structure. Let's briefly discuss what primary, secondary, tertiary structure of a protein are. So, when sequential arrangement of amino acid that form peptide bond, they are called primary structure protein. They basically form a chain like structure, like L, I, A. They together form this, and there's peptide bond among each of the amino acid. They're called primary structure. The secondary structure is generally made up of hydrogen bonds. This is from CO coming from one of the acid. So like alpha helix or beta, beta sheet, beta pleated or beta sheet structure. What happens is CO from one of the peptide bond forms a hydrogen bond with NH of the one lying below it. That would form alpha helix, and in sheet you can see they form this kind of structure. So that's again secondary structure. The further folding of a protein is called tertiary structure, that gives the protein the 3D shape. Now, this 3D shape makes the protein functional, and it's generally from disulfide bond between them. The tertiary structure is basically formed between the uh, you know, side groups of the amino acids after the secondary structure after the folding. So that they become a 3D structure, that's called tertiary structure. The further folding of tertiary structure makes a cleft and you know subunits, that's called quaternary structure. Not every protein has quaternary structure, some do, and the examples are like hemoglobin and things like that. So yeah, very good. Let's move on to the next question. The gel polyacrylamide gel electrophoresis of, yeah, the the polyacrylamide gel electrophoresis of protein is based on following properties of protein. So and let's see what this page is. Gel electrophoresis is used for purification of proteins. And now let's discuss what page actually is. I've made this little diagram for you to understand. Maybe I can just draw it here. Yes. What happens is, you know, let me make this well. Now, gel electrophoresis, they have this gel And the gel here has been specified polyacrylamide gel, which is very inactive gel. It does not react with the protein. This is actually, connected with a source of battery. Let's say a battery here. This battery, under the, oh sorry, this is kept in a box as well. This battery charges it, and this one becomes cathode, and this one becomes anode. What they do is they have this sample size. They put the protein here. The protein, as you know, has different charges based on the side chains that they have: positive, negative, positive, negative, like that. What they do is they basically denature this protein to get a primary structure. You know, they how do they denature protein? They denature using detergent, some kind of detergent. Let's take the example of SDS, but because they are not being very specific if they are using SDS page or not, I'm not um, I'm not specifying it. Let's just assume that they have used some kind of detergent, and now this is denatured. After denaturing, what happens is the charge. Suppose there are different charges, plus minus. This detergent imparts negative charge everywhere, and there can be different kind of protein. It can be heterogeneous, it could be homogeneous. What they do is they take the sample, they pipette the sample. I'll take here, they fill it here, and there's a buffer in this. They fill it. The gel is then put into a container. The container is filled with buffer, and generally here is a marker protein. We know the size of this marker protein. It just gives us a rough idea of, what kind of protein size it is, like 50 Dalton, 70 Dalton, 100 Dalton, 110 Dalton, something like that. And when the electric field is applied towards it, the cathode becomes, obviously cathode is negatively charged, anode positively charged, and this anode is negatively charged. I'm sorry. Ugh, no. Sorry. Yes. Oxidation takes place at anode, and a reduction takes place at cathode. Now, under the influence of electric field, the protein, after denature and breaking, protein starts moving based on the size of the protein. The smaller one moves faster, and it comes faster towards anode, and the larger one, they show lower mobility, slower mobility, so they remain up. So the larger one stays here, and the smaller ones move forward. So based on charge, and it should not exactly be charged, because the charge is more or less same once we use um, detergent or something like that. It should be size only, but considering everything, it's size and charge. This option seems the best among the following. So yeah, let's move towards the next question. The minimum number of residues that appear to be necessary for a polypeptide to fold into a discrete and stable shape that allows it to carry out a function is near 40. Very good, guys. Yes, very good. It's actually true. Because after it has 40 residues, then only it becomes like, structurally. Yeah, true. Everyone is correct. It is true because the folding becomes more efficient, and it's based on a study. They did the study. There was a few exceptions. They're called mini proteins that were able to fold, but in general, and you know based on PNAS study, it has been confirmed that you actually need around 40 residues for a polypeptide to fold and make a stable shape. Let's, let's move on to the next question. Now let's revise. We are done with the assignment from first week. Now let's have a brief summary of what was taught in second week: enzymes and its function. Now, what exactly are enzymes? Enzymes are basically catalyst, the bodily catalyst that increase the rate of reaction, you know, taking place in biological uh, organism and biological system to, like, not just 100 times, like 1,000 times. It's so efficient, more than any catalyst that we have been able to design. So, how does an enzyme actually work? I'm just going to read a definition just for the sake of clarity and clear communication. An enzyme acts to lower the activation energy by helping stabilize the transition state. The energy of the substrate and products are both unaffected, and therefore equilibrium ratio of substrate to product is unaffected. Now this is very important because what enzyme does is it catalyzes both forward reaction and backward reaction as well. It does not exactly change the energy of the start forward reaction or backward reaction. What it does, it is it stabilizes the transition state here would be the enzyme substrate complex, what they form. And once that is stabilized, the activation energy lowers down, and that increases. That is the main reason why the formation of this new transition state, it's so low, the energy is less, and hence it's easier you know for the enzyme to increase its turnover and hence catalyze the reaction. Enzymes are proteins. Obviously, not all enzymes are proteins. There are some enzymes that are not proteins. They're ribozyme, that's not protein. But in general, most of the enzymes are proteins. Enzymes are proteins which act as body's catalyst agent that speed up chemical reaction without themselves being consumed. Yes, most of the enzymes are not. They are catalyst. They remain as they were before the reaction start. But honestly, there are few examples in which enzymes kind of change their. Yeah, I think in upcoming lesson we'll read more about those enzymes. But enzymes in general stay as they were before the reaction start. They are not involved in the reaction in themselves. They they catalyze the reaction, they provide the surface area, they stabilize the transition state. That's how enzymes work. Now let's see the graph here. This graph is very important. Why so? Let's see. You see, this this is the free energy, and without enzyme what happens is the starting material and the product, you see, the product is more the product form because it is favored. So once the product is favored, the energy of the product will obviously be lower than the starting material. That's how it is. The difference between the energy of starting material and the product's delta G and activation energy, they have to cross over this particular energy barrier for for the substrate to get converted into product. That is called activation energy. Enzyme works on it. Enzyme basically lowers down the activation energy by stabilizing the transition state, and once it's stabilized, you can see there's an alternate pathway for that, for the starting material to reach the product, and hence by lowering down the activation energy, enzyme catalyzes the reaction. Now let's, what happened? Yes, is there any question? If not, I'll just uh, proceed. Which of the following is not a property of enzyme? They increase the activation energy of a reaction. B. They are highly specific to their substrate. C. They remain unchanged after reaction. D. They work by lowering the activation energy. We just discussed this concept. Take your time and read it. Good. I'm already getting the correct answers. Yeah. So let's discuss each statement on their own. Um, Obviously, enzymes do not increase activation energy, they do quite the opposite. They decrease the activation energy by stabilizing the transition state and lowering the activation energy. So they are highly specific to their substrate. Yes, obviously, enzymes are very, very specific. They do not, one enzyme does not catalyze all kind of reaction. They're very specific. they they will we'll read about their mechanism in the upcoming slides, but they have this particular affinity towards their substrate. They catalyze a particular reaction very efficiently, hence they are very specific. They remain unchanged after reaction. That's true. They once the reaction is done, enzyme are left with what they started, are left in the condition in which they started. So yes, they remain unchanged even after the reaction. They work by lowering the activation energy. That's again true, and hence A is option. That's not correct. let's let's see the second question. The active site of an enzyme is responsible for A. Binding to inhibitors permanently. B. Binding to a specific substrate and catalyzing the reaction. C. Changing the pH of the reaction medium. D. Increasing the temperature of the reaction. Now, let's see what active site actually is. All of you are quite right. It is B, binding to a specific substrate and catalyzing the reaction. Very good. Now, what's active site? Active site is basically a cleft. Once you form a secondary structure, you form a tertiary structure. Now, this tertiary structure is a 3D structure, which is further folding of the secondary structure. Once that happens, is there's some kind of cleft. This cleft, and this cleft is generally more hydrophobic. what happens is different, there are different exposed side chains, and from different amino acids, and they are like you know um, protruding out. Now this make this cleft is where these enzymes go and bind, and they catalyze the reaction. They the different side chains of in the hydrophobic cleft of the active site, that's called active site, they react with this enzyme, they form this enzyme substrate complex, and they catalyze the reaction. Again, let's briefly see what it is, how the enzyme catalyze the reaction, the process of enzyme catalysis. The enzyme, we discussed about the active site. What happens is the substrate comes and enters the. So there were two hypotheses. I don't think I've put it here in my slides. They were earlier, they used to think they have this hypothesis called lock and key hypothesis by Fisher. What they thought was that active site is a fixed site, and the substrate is quite complementary to the active site. So if this is the structure of active site, the the substrate will be of the complementary size, and it will just go and slide in there. They'll form a very strong bond, and that's how reactions are catalyzed. That's how lock and key work, like how there's a key, just one key for one lock, right? Once it gets there, it just locks, it just forms a very stable conformation, and the reaction is catalyzed. That was one hypothesis given by Fisher, and it worked for quite a while. It was quite agreeable for people to accept that hypothesis. But there were many cases in which people saw that active site is not a fixed, there is no fixed conformation for active site. So let's discuss this, and then we'll discuss the induced fit hypothesis. The enzyme, along with this active site, is and the you know is sitting there. The substrate comes and tries to lock into the enzyme. Once the enzyme and substrate are locked together, they form enzyme substrate complex, and the substrate is then converted into product. The product is released, and after the release of the product, the enzyme regains its original position. Now the active site of enzyme is again open, and for it to catalyze the next set of substrate. Yeah, here it is. Now let's discuss induced fit hypotheses. We discussed the lock and key one. In induced fit hypothesis, what they suggest now, we follow this hypothesis now, and it seems to be a better explanation, that it seems to explain things more cohesively than lock and key hypothesis. Once the substrate, there is active site, once the substrate comes, the active site, the enzyme has this substrate comes there and induces some kind of fit, like a change in orientation and conformation of the active site in the enzyme, and the enzyme itself induces some kind of change in the substrate. They try to position themselves better in a way that they both fit each other properly. They don't have any fixed shape to come and uh, fit, but instead they are both influencing each other to get a better fit of the idea. Now there's an example of induced fit here. You can see in the above option, you see here the distance for hydrogen bond is quite big. Yes, van der Waals force, ionic bond, everything is there. suppose this is a substrate and this is present in active site. What it does is it's trying to change and accommodate in such a way that it's easier for them to form hydrogen bond, right? See, distance is an important factor in formation of hydrogen bond. So what they do in this induced fit is they try to change and try to come to a conformation where they form a better, where they increase the probability of forming the bonds in a better way. So this, I'm sorry, I'm sorry. So now the ionic bond, you can see how this changes from this ionic bond to this, and from the hydrogen bond shown here to this. They're both, they're actually trying to fit in a better way, and that's when the enzyme and substrate complex formation takes place. They care in, and how the enzyme catalyzes this reaction and how product formed. Now, there are different ways in which this can go on. One of the very basic reaction is acid-base catalysis. Now, acid-base catalysis is often done when there is some kind of base present. We know there are some few basic acids, and of which like histidine is important. And generally, acid-base catalysis, histidine is present because of the presence of imidazole ring. It's basic. So let's see the example here. You can see this is the imidazole ring, and the enzyme is connected to this one. There is a lone pair in nitrogen there. What it can do is, I'm sorry, what it can do is this lone pair can accept H plus, and then again this reaction, how this is simple organic chemistry. The lone pair from this nitrogen uh, comes here, and this one moves here to neutralize the charge here in nitrogen. That's after accepting the H plus. Now they form a resonating structure together, and now you can see how this acid base reaction is working on. H plus is being taken by the imidazole ring, and that's how they are trying to catalyze the reaction. Same can be done with glutamic acid in case of HMG, coenzyme A reductase, and aspartic acid can change into aspartate, and that's how you'll read more about this in the upcoming lessons, I think, about the triad serine complex and the triad. So this is how acid base catalysis. The next mechanism is nucleophilic groups. This one is very interesting. Here you'll see how things work on. This is a triad. You can see serine, histidine, and aspartic acid. This is basically aspartate. You can see how they're working together is very beautiful. This aspartate, you can see, is trying to hold this histidine. The carboxylate here is in holding this one in a particular orientation, so that it's not free to move. It just holds it there, and with a formation of simple hydrogen bond, it's basically fixing the conformation. This conformation, when fixed, what it does is this lone pair is ready to accept the hydrogen from this OH, and once it does that, the lone pair here, along with negative charge, you can see, can easily attack there. So let's see. The aspartate is holding that histidine together, and the nitrogen, the lone pair from this nitrogen, is ready to attack this H, like act as a base and extract this H. Now this, once after forming that tetrahedral intermediate, it wants to neutralize the positive charge on its own. So what it does is it lets the nitrogen take the edge to neutralize the positive charge in it. Now you can say nitrogen has positive charge, and this one they have formed this tetrahedral, not exactly tetrahedral in this case, but yeah, you can see there is four bond here. The carbonyl oxygen would like to be back in its double bond. So what it does is this negative charge will come back here, and this bond will try to extract H and leave NH2. That's what it does. You can see this one is leaving here, and the nitrogen here is again uh, neutralized. It has got its lone pair back. Now I've told you that this one is very hydrophobic. Now solvents are, because it's a biological system and it's happening in the body, water is easily available there. Now this molecule of water, what it does, it again it attacks the carbonyl C, and you see there's an A reaction here. Again, the negative charge would like to come back and leave it as it is, try to neutralize it. And you see, this is all simple organic chemistry. There's one trying to neutralize the charge that it already has, will lose its H. Nitrogen lone pair will again uh, try to have this H here, and in order to neutralize the positive charge on oxygen, it will lose its H. Again, now the nitrogen will have the hydrogen, and because it wants to neutralize itself, what will happen is this bond will come here and they'll try to lose this. And now what you have is carboxylic acid here. Again, this is back to its original position. It has catalyzed this reaction, and again the enzymes, everything is back to its own position. You can see the beauty of this triad, how they're helping each other fix in a stay in a particular conformation where they can, with the help of acid base catalysis. A part of it is actually acid base catalyzed as well, but the main reaction happening here is nucleophilic. The carbonyl, how the carbon and gets attacked, and the different OH from serine attacks it, and how everything works on. So yeah, that's how this works. And the group together, they have a very beautiful relation where they try to keep each other in a fixed conformation and catalyze the reaction. And after the reaction is done, they're back on their own as they are next. Yes, I'll share this slide, my Google Drive, and you'll be given that with the NPTEL people will share the link of the PPT as well as the recording of this live session with you guys. So don't worry about it. You'll get all this PPT. Let's discuss about the cofactors. Now, what are cofactors? We see how it's being catalyzed, acid base and nucleophilic groups. Cofactors are like additional non-protein structures, substances, um, that that's basically important for the reaction to happen. They, without cofactors, you can say the reaction won't happen. They are either metals or small organic compounds, non-protein. You have to remember, sorry, these are non-protein substances. This is the most important part. Additional non-protein substances, they can be either metal or small organic compounds called coenzymes. Most of the coenzymes, they have like ionic bond, non-covalent interaction. Covalent interactions, why they don't prefer covalent, because this has to be reversible, right? If you form covalent bond, it's very difficult to break covalent bond. So even for medicine, we prefer non-covalent interaction because those reactions are reversible, and it's easier to break them. We don't want any kind of like permanent change in the body, and that's how these enzymes work as well. They generally work with hydrogen bond, very few of them have ionic bond, but in case of cofactors, there are some ionic bonds taking place as well. But yeah, mostly the coenzymes are bound by ionic bonds and other non-covalent bonding interaction, but some of them are covalently bond and they are called prosthetic groups. You'll be asked a question, which of the compounds, once they are covalently bond, what are they called? So you have to remember they're called prosthetic groups. So let's see an example here. Here you can see lactic acid with NAD plus. Now the enzyme here, this nucleophilic enzyme, it would try to take the H. Now this one, how it's being catalyzed. Keep an eye here. Observe the change happening here. What it's doing is, like, once it forms this one, this tries to gain the hydrogen. The hydrogen, once it's gained, the driving force here is the positive charge in nitrogen. It does not like to stay with the positive charge. It wants to neutralize itself. That's the driving force here. Now you can see, after uh, trying to extract H, what it does is it gains its neutrality. It has additional hydrogen and 2 electrons. That's how it works. Now NAD plus is converted into NADH. Lactic acid is converted into pyruvic acid. Let's take a question here. It was from your assignment in week 0 assignment, just for a very basic interaction. The conversion of NAD plus to NADH is an example of reduction because A, the pyridine ring loses electrons and a hydrogen. The pyridine ring gains electron and a hydrogen. C, the adenine ring loses electrons. D, the adenine ring gains electrons. You guys remember the structure of purine, pyrimidine, things like that, right? The structure here, what does this remind you? Anyone would like to answer this question? You just discussed it. Perfect. Yeah, that's the right answer. NAD plus takes a hydrogen, gains a hydrogen here, and 2 electrons, and gets converted into this one. This one gets reduced. NAD plus get reduced after accepting hydrogen, and it oxidizes lactic acid to pyruvic acid. You can see how the alcohol here, OH here, is getting converted into ketone. This is secondary alcohol. You can see how this is a secondary alcohol. Secondary alcohol on oxidation gets converted into ketone. Now once this one, lactic acid, is oxidized to pyruvic acid, NAD plus is reduced to NADH by gaining 1 hydrogen and 2 electrons, and hence the structure. So yeah, option B is correct. Very good. Let's move on to the next question. Which type of enzyme inhibition occurs when an inhibitor binds to active site, preventing substrate binding? Very good. Yeah, the options are competitive inhibition, non-competitive inhibition, uncompetitive inhibition, and D, allosteric activation. Yes, everyone is correct. The answer is option A, competitive inhibition. In competitive inhibition, what happens is, there is active site and the substrate has to go and bind to the active site. Now what happens is, in order to inhibit this, the substrate, the inhibitor, what it does is, instead of letting the substrate come there, it goes and binds in place of the substrate, and hence it does not let the substrate bind to the active site. And once the substrate is not bound to the active site, does not get to bind with the active site, it is unable to catalyze the reaction. And if it does not catalyze the reaction gets inhibited, the reaction stops, and that's called competitive inhibition. Let's have a look at what are different kind of inhibition. So one is competitive inhibition. In competitive inhibition, what happens is, there's substrate and inhibitor. Inhibitor competes with substrate to bind to the active site, does not let the substrate bind to the active site, and hence inhibits the reaction. In this reaction, increasing the concentration of substrate, once you increase the concentration of substrate, you can reverse this reaction because there is more competition. The competition, अगर substrate ज़्यादा होता है, I'm sorry, if the substrate is more, the probability of the substrate going to the, and binding to the enzyme is more. And um, you know that's one way of making this reaction reversible. The other way is decreasing the concentration of inhibitor. So if there is less inhibitor, the chances of it going to the active site and binding is less. Hence, substrate is free to bind with the active site of the enzyme. In uncompetitive inhibition, now there can be confusion in uncompetitive inhibition and non-competitive inhibition. In non-competitive inhibition, inhibitors can bind to enzyme alone as well as enzyme substrate complex. But in non-competitive one, you can see there is option. See, it can bind to the um, substrate alone, the inhibitor, or even when the enzyme substrate complex has found, the inhibitor can still bind to it. That's the key difference between uncompetitive and non-competitive. In competitive, what happens, it binds particularly to the enzyme substrate complex and thereby stops the catalysis. In non-competitive inhibition, the Km remains the same, Vmax decreases, and in uncompetitive, Vmax as well as Km constant, they both decrease. Now we'll discuss about this Km and Vmax when we discuss Michaelis maintain constant. Okay. I forgot to put animation in this one so you can see the correct answer. But try to ignore the answer. I'm sorry. Yeah, I've muted Mr. Sham. I think he accidentally unmuted himself. Okay. So the Michaelis-Menten constant Km is defined as A, the substrate concentration at which enzyme activity is at its maximum. B, the substrate concentration at which the reaction velocity is half of Vmax. C, the amount of enzyme required to convert all the substrate into product. And D, the rate of enzyme denaturation. Think about it. This is more or less a revision kind of thing because all this has already been taught in the weekly session, in which sir has uploaded, the videos and PPT and everything. I'm assuming that you have been through that already, and this is just to brush up on those concepts, just to help you revise all those concepts. So read these options and you know give me the correct answer. So the correct answer is the substrate concentration at which the reaction velocity is half the Vmax, you know, Vmax by 2. Let's discuss what Michaelis-Menten constant is. What is it? So instead of deriving everything, I'll just ask you guys to remember this equation. V naught is equal to Vmax. V naught is equal to Vmax concentration of S Km plus concentration of substrate. Now Vmax here is the maximum velocity with which this reaction can be catalyzed, maximum speed with which the reaction is going on. V naught is the essential, initial velocity. Its unit is moles per second, per minute, per hour, depending on the question that you are given. S is the concentration, substrate concentration, again it's in molar. Vmax is the velocity with which, the maximum velocity with which the reaction can be catalyzed. Km is substrate concentration. Now you can see here, look at the graph. You see it's rate of reaction versus substrate concentration. See, if this is Vmax, this is half of Vmax. Now plot it here and you see the concentration of the substrate at which the Vmax is half. It's called Km constant. That's Michaelis-Menten constant. Understood? Remember this equation, it's very important. What happens is, when during the initial time, the reaction is slow because there is not much of the concentration of the substrate. Less substrate, slower the reaction. As the concentration of the substrate increases, the rate of the reaction moves very fast in a hyperbolic curve. It keeps on increasing until a point where all the active sites are filled with substrate. It reaches a saturation point where there is no longer active site or enzymes left for a substrate to fit into and to be catalyzed. So at one point, the increase in the concentration of substrate does not lead to any change in rate of reaction. The reaction will go on once it's saturated, once you're full, your tummy is full, no matter what the food is lying in front of you, you cannot eat it because your stomach is full of food. So that's what happens with enzymes. Once they're all saturated with substrate, they no longer need more substrate to catalyze the reaction. Let's go back here and see the question. Michaelis-Menten constant is defined as the substrate concentration in which the velocity is half the Vmax. Clear? Now let's move on to the next question. Which of the diagram illustrates the way in which the rate of an enzyme controlled reaction depends on substrate concentration? We just discussed this. me an answer. This one is a very simple one. Very good. Yeah, the option A is the correct one. Very good. You see, again, I'll just uh, repeat it once again. When the concentration of the substrate is less, there are there are lots of enzymes with the active site, lots of enzymes available. They have free active sites. So the less, when the concentration of the substrate is less, they're very hungry. They try to catalyze the reaction. The rate of reaction is very slow, and they're very hungry. It goes slowly at one point when it's the rate of reaction moves very fast as the concentration of the substrate keeps on increasing. They're hungry and they try to catalyze this reaction very fast, but at one point, when they reach the saturation, there is no longer any enzyme available to catalyze the reaction, because all of them have their substrate they're working on, and the amount of substrate, increasing the concentration of substrate won't lead to any change. That's called saturation, and this is the hyperbolic curve. This is the correct answer. That's like, this is a typical graph of enzyme catalyzed reaction. Let's move on to the next question. What effect does a non-competitive inhibitor have on enzyme activity? Non-competitive inhibitor. We just discussed the three types of inhibition: competitive, non-competitive, and uncompetitive. Think about it. What effect does a non-competitive inhibitor have on enzyme activity? A. It increases Vmax. B. It decreases Vmax but does not change Km, that is Michaelis-Menten constant. C. It increases Km but does not change Vmax. D. It competes with the substrate for the active site. No, option D cannot be right because obviously it's non-competitive. It's not competitive. It's not competing with the substrate for the active site. If would have been the case, it won't be non-competitive. It would be competitive. So D, you can just cross D on this one. It increases Km but does not change Vmax. That's not possible because Km is the one in which Vmax is half of the. I can see two options here, like people are going with B and C. Good. The correct answer is B. It decreases Vmax but does not change Km. In non-competitive inhibitor, in case of non-competitive inhibitor, it can bind to both enzyme alone as well as enzyme substrate complex. It does not bind to the active site on its own. Yes. Is there any question? I would assume no, and I have to move forward. Okay. In non-competitive inhibition, it binds to the allosteric site. What is allosteric site? Allosteric site is actually another site apart from active site. There's another cleft now in which inhibitors can bind. Allosteric. Wait a minute. I'm sorry. Yeah, so it binds to allosteric site. Now, allosteric site is another site apart from that, in the site that's exposed. Like, suppose if this is active site and this is enzyme, I just draw it here. If this is the active site, this one is going to be the allosteric site. Allosteric site. Now this allosteric site, what inhibitors can do is, inhibitor can go and bind there. Once they bind there, they will change the structure of, change the shape of the um, active site. Now this active site can, the substrate coming for the active site can no longer recognize the active site because the shape of the active site has changed. Now the substrate no longer recognizes the active site, and it just goes on. So for in order for the reaction to be catalyzed, the substrate has to come and sit in the active site. If it's not doing that, that means the reaction is not being catalyzed, and once the reaction is not being catalyzed, it is practically inhibited. So that's what happens with allosteric inhibition. you know it decreases the enzyme efficiency, and once the efficiency is decreased, you can see the speed with which it was once catalyzing the reaction, it slows down, right? This slowing down of the reaction will bring down the Vmax, but the Km constant won't change. It remains unaffected because you know the enzyme concentration, no matter how much you increase the substrate concentration, it's not going to change because the substrate is no longer recognizing the active site. So changing the concentration of substrate won't change anything. So Km remains the same, but there is decrease in Vmax. Hence B is correct. You guys got it right. Now, or should I repeat it again? If there is any confusion, please let me know. I can repeat it again. Maybe unmute yourself or just type it. Yeah. Okay, yeah, sure. So in non-competitive inhibitors, uh, they are not competing for the active site. They're just binding to allosteric site and changing the conformation of the active site. Okay, in uncompetitive inhibition, what happens is, once the enzyme substrate complex is formed, only then the inhibitors come and, you know, uh, inhibits the reaction. Don't think about anything else, because if it will just increase the complexity. Just remember the key difference here between non-competitive and uncompetitive. Non-competitive, going to allosteric site, and it binds whether or not there's substrate or not. If the even if without substrate, it can go and bind in the allosteric site and and can change the active site. But in uh, in uncompetitive, it first lets the substrate come to the active site, let it form enzyme substrate complex, and then the inhibitor binds to the um, you know enzyme substrate complex. You understand it now? Yes. Yes, yes, yes. Yeah. In case of non-competitive inhibition, Vmax decreases, and the Km remains the same, because the concentration of substrate does not lead to any kind of change. But in case of uncompetitive inhibition, Km also decreases along with Vmax. For example, uh, Km is basically indicative of how good the affinity of the enzyme is towards the substrate. So suppose a vehicle a vehicle needs a vehicle that needs less amount of fuel is better, right? It performs better. We say, oh, this the mileage is good and it consumes less fuel, so that one is better. In this case, the you know this the vehicle is not moving, so the km is very less, vmax is very less, but efficiency is also very less, right? So just uh, think that, keep in mind the example of allosteric site. Remember, in case of allosteric binding, km remains the same, vmax changes. But in uncompetitive inhibition, km also decreases, concentration also, km also decreases, and vmax also decreases. Is it okay? Okay, thank you. Let's move to the next question. If an enzyme follows Michaelis-Menten kinetics, what happens to the reaction rate when the substrate concentration is much higher than Km? I'll repeat this question again. If an enzyme follows Michaelis-Menten kinetics, what happens to rate reaction when the substrate concentration is much higher than Km? A, the rate of reaction the rate remains constant at Vmax. The reaction rate decreases. The reaction rate increases indefinitely. The enzyme stops working. Think about the equation that we have. Actually, that won't change anything because we already considered Vmax is when the concentration, the enzymes are saturated with the substrate. So increasing the concentration is not going to change Km. It's already saturated, so no amount of changing the concentration of the substrate is going to change Km. So yeah, option A is correct. Now let's solve this question. What is the ratio of V naught by V max when substrate concentration is equal to 5 times Km? Yeah, very good. Let's solve this. Let's just write the equation. Michaelis-Menten constant. We know V naught is equal to V max concentration of substrate by Km plus concentration of substrate. Right? This is the equation that's called Michaelis-Menten equation. What we can do is V naught, we can bring the V max here. V max. Now concentration of the substrate by Km plus concentration of the substrate. We know the concentration of substrate is 5 km, so I'll just replace it. Concentration of substrate is 5 times km, 5 km plus km plus 5 km V naught by V max. No, V naught. Am I audible?
Yes, ma'am.
Okay, thank you. V naught by V max is 5 km plus 6 km. You can just remove km. Now we're left with 5 by 6. Simple. Therefore, V naught by V max is 5 by 6. Did you guys get it? It's a simple, but if there is any doubt, please let me know. Is this okay? Now, this brings us to the conclusion of this problem solving session. I hope you guys understood more or less all the things that I tried to explain. If there's anything, please let me know. I'll try to explain everything. You can also post your questions or any doubts in the forum, or you can email me. This session is recorded. The link of this session, this recording will be sent to you along with the PPT by NPTEL authorities. They'll send it to, you know, how they send you all the assignments and everything. So yeah, I hope you guys understood everything.
Yes, ma'am.
Okay, perfect. So is there anything you'd like me to repeat, or anything, any doubt that you have? If not, I'll conclude the meeting. Thank you, everyone. Uh, I'll see you in the next session. Hopefully, you guys complete all your lessons by then. And if you have any question, please, um, make a point of sending me those questions, and I think I'll try to answer everything. Thank you. Bye.
Thank you, ma'am.